into the total electric field. Let me write the things. Okay, so the properties of this diagram are as follows. A vector drawn from the origin to any point, in this particular case 0.8 for our example, represents magnitude and phase of this equation. So the red line that we have seen before is the vector, is a vector, it is magnitude and phase. And you should have it on your Another interesting property is that the absolute value of the electric field, that is really what we are looking for, is proportional to the length of the vector, of the blue vector that you see there, drawn from this point one to the point that represents B. It is this one. So, what is picture telling us? It's telling us that if you move closer to this point, you keep on going in spirals. But if you get closer to this point, the amplitude of the electric field is getting smaller and smaller, weaker and weaker. This happens because the V parameter is increasing. If you look at the expression, I will write it again for you there because it's under the board. But you have it on your notes. V is equal to H to the 1 plus the 2 divided. Now, for a given geometry, V increases when H increases. That is, if the obstacle becomes higher and higher and higher, you move closer and closer and closer to this point, and your electric field reduces speed. Zero means that the obstacle is just touching the baseline between the two stations. And then V can be negative. A negative value of V means a negative value of H. Means obstacle smaller, lower than the baseline, below the baseline. And if the obstacle is smaller, you end up, and you can see that at the end, you will end up on this point. And this is the strongest electric field that you can have, and that is equal to the free space. Okay, is there an easier way to show these things? Yes. If we look at in particular at the extra losses, if you are interested in, sorry, before moving on, any question? This could be a good sign, or this could be a bad sign. It's a bad sign. More useful for us engineers are the extra losses due to this situation with respect to free space. So we have to, in other words, what we are interested into at the very end are the extra losses in dB because if we have this number, we can easily calculate free space field, and then we can correct it with the extra losses. So more useful for our application is this graphic that really shows this. What do we have here? Those are the extra losses. So negative losses means amplification, stronger field. And positive losses, dB, means attenuation, lower field. As a function of the V parameter, that is, of the function of our geometry. There are a few interesting things in here, and one is if your obstacle just touches the baseline, that is, if you have transmitter and receiver, and your obstacle just reaches the baseline, but actually A and B see themselves. This situation, as I told you before, corresponds to B equal to 0 because H is 0. If you look at the extra attenuation that you find an extra attenuation of 60 dB. You have extra losses. In this situation, the electric field that you are receiving is 1/2 of the one or the field that you would receive in free space, even if there is a direct visibility, geometrical visibility between A and B. You lose 60 dB. Why? What is the physical reason? Why are we losing? Why is our signal half the signal that we will receive in free space? Even if the two are, there is a line of sight between the two. If you think about diffraction, if you think about Huygens equivalent sources, you will find the physical reasons for example. This happens because our obstacle is blocking out of the sources. Those one here are blocked. So only those Huygens sources contribute to total electric field. That is, you receive half of total electric field that you receive in free space. So you are here. Please know that 0 is the free space level. So this 0 is what you would receive if there was no obstacle. So you are here, and you have to go quite a long way before you receive a field that is comparable to this space. That is, you have to lower this obstacle quite a lot with respect to the baseline before you reach a point where the electric field is comparable with what you receive in free space. Why? Why do we have to lower negative values of V means negative H means lower obstacle? Why do we have to lower the obstacle? Because we have to free the first Fresnel ellipsoid. Any object entering the first Fresnel ellipsoid will cause you a strong reduction in the receiving field. There is still some focusing effect here. For this particular value, you receive a field that is stronger than you would receive in free space. But this is a minor effect, also because we are not worried of stronger signals. We are worried about weaker signals. And then when the obstacle becomes very small, the things converge to free space. And this was one side of the problem. The interesting thing is that now if you consider positive obstructions, that is obstacles whose height is higher than the line of sight, you move from this point downwards. But the field does not go to zero abruptly. You still get, with not very large attenuation, we are talking 16, 20 dB, this is 24. So even if the obstacle is higher than the baseline, you can quite often make the radionic. Again, what is happening is that who is contributing to the receiving field? All the unblocked Huygens sources that are radiating somehow some energy towards the receiver. And we will use this graphic or the equation that I'm going to give you to design the radio links when we have some obstacles. One obstacle in particular. Multiple obstacle is more complicated, it's just questions? Yes. Okay, this graph is okay, but more handy if you do calculations are the so-called Lee approximation.
we don't consider the width of the structure.
Yes, because the knife edge model assumes that the obstacle is very thin and it is very sharp. So if the obstacle is wide, then we have to do something slightly different. Also, if the obstacle is round, I will discuss this later. Okay. So this is a model for obstacles that you can model this kind of obstacles. For example, corners of buildings. So if you have, let's just anticipate, if you have a building like this, you model this, you take this and take this, and you model this thing like two knife edges. You just model the corners. But we shall see this later. Okay, Lee, what did Lee do? But he just obtained a set, nothing special, he just obtained a set of interpolating functions that actually reconstruct this curve. I will give them here, then they are on the book, but you will find this. Well, maybe I just project that. This kind of since you have them on the book, I just project them so you can. There is no need for you to copy them. It's just a set of equation. If you don't have, they should be on the book anyway. Should you don't have them, I can send the file to you, but it's so. Those are for different values of v, of the parameter v. But what they really do, simply do, is to interpolate that figure, the diagram that we have seen before. So to apply those equations, you first, as usual, calculate the Fresnel-Kirchhoff parameter for the geometry. Then, according to the value of the Fresnel-Kirchhoff parameter that you find, you choose the right equation. And what you get out of this equation is the extra attenuation in dB that you must add on your link budget with respect to free space. Those are on the electronic copy of the book. If you need, I can send it to you, but it's already there, so I will not go too much into details of that. We shall use them. That's it. Questions? Okay. Okay, what happens if and now we have considered very sharp obstacles. What happens if you have a round obstacle, like for example a hill or something anyway whose shape is rounded? You have an extra loss, unfortunately. Losses are higher. So let's assume that you have something like that. A rounded obstacle. You first calculate the insertion losses due to a knife edge. And then you add an extra contribution. There are several analytical approximations. You will find on the book, you will find several of them. One that is quite common is this one. Those are empirical equations, so there is no, we cannot try to derive them from the electromagnetic theory. There are approximating equations that work well, but you lose the physical meaning of the equation. Nevertheless, those are extra dB of attenuation, extra losses. That depends on the lambda and on the radius of curvature of your round obstacle, and on the angle alpha. So if you have the geometry, you calculate the losses due to knife edge blockage, and you, on top of that, you add those extra losses due to the round shape. The round shape, unfortunately, introduces stronger losses than sharp shapes. Okay, that's for the single obstacle. Now we move. If there are no questions, we move to multiple obstacles. That is the more frequent situation when you are, for example, into a urban environment. You have multiple buildings, multiple obstacles that can be modeled as multiple knife edges. So that's what we do. Questions first? No? Yes, it is. Okay, when you have multiple knife edges, the theory is not as simple as the one that we have seen before. So we will not even try to use a rigorous approach. We use some empirical approximations, things that work in things that work. They are not extremely precise, but they do the job. We will see two of them. One is simpler, but less accurate. Another one is more complex, but more accurate. So the first method is the so-called Epstein-Peterson. From now on, we will often use empirical methods. Those empirical methods have been then implemented into recommendations. I will tell you what the recommendations are, but really the recommendations are very simple recipes where you put in the number and you get the result. But it is important that you understand why you get the result out of those methods. That's the reason why. Now, what the F10-Peterson method, what is this method? Okay, so we have a transmitter. Again, the transmitter and receiver are irrelevant. Who is transmitting and who is receiving is irrelevant. And let's imagine that we have 3 knife edges, 3 obstacles that you can model like knife edges. Actually 4. Each one with its own height. The Epstein-Peterson method, as a first thing, as a first step, asks you to apply the so-called tight rope to the profile. The tightrope is, you imagine you take a rope from the transmitter to the receiver. Right, one choice. Okay. Like this. And the rope must be tight. You pull the rope and see which obstacles are touched by this tight rope. So you can discard obstacles not touched by the rope. So this obstacle can be ignored. And then you start working on the remaining obstacles. So let's number them for convenience. So this is obstacle number 1, this is obstacle number 2. We don't consider this. So this is obstacle number 3. What you do in this method, you consider one obstacle at a time. You calculate extra losses for this knife edge obstacle, then move to the next. I will show you now with this example how we do it. So, we take the first obstacle number 01, and we consider the extra losses from the transmitter to this second obstacle due to this one. That is, we draw a baseline from the transmitter to this obstacle, and the height of obstacle 01 for this configuration is this small segment here. And we treat this as a single knife edge obstacle. That is, from H1, from the geometry, we obtain D1, that is the Fresnel-Kirchhoff parameter. And we have then the losses from due to the obstacle 01. Those will be dP. Okay. Any doubt about this procedure? Then we move to the next obstacle. So let me clean up here. You can do another drawing on your. Now we take into account contribution of obstacle 02. We apply this from the obstruction between 01 and 03 due to 02. So we draw a baseline between 01 and 03. And the height of the obstacle is not the total height, as we said before. We already seen this, but the height of the obstacle will be, as usual, the distance between the top of the obstacle and the baseline. So we have H2. We get Fresnel-Kirchhoff for this obstacle, and then we get more losses in dP due to the second. Well, now you got the logic of the game. We don't consider this, so this is not existing. So next contribution will be blocking due to obstacle 03 between 02 and receiver. Again, let me clean up. Okay, so now this case is particularly unfortunate because baseline is difficult to know, but nevertheless, we draw the baseline. And we end up H3. And okay, you know that, you know the game. Total losses will be just total extra losses will be just the sum of the three contributions. Now this method is very simple to apply once you know the mechanism. Now there are pro and cons. Pro is that is very simple. Cons of this problems with this method. Mainly two problems. One is not very accurate. When you have more than 4 obstacles. And it's not very accurate when the obstacles are very close to each other, closely spaced. In particular, it will tend to predict very large attenuation. That is not necessarily realistic. If this is the case, we have to sort out to a different method that is slightly more complicated but more precise. Before we do that, questions?
For example,
Yes.
calculate the first loss. What's the distance between the X and dot?
And the obstacles? And 2. This geometry obviously is exaggerating the geometry. In principle, you should consider this distance. In practice, you can consider this because usually the distance between the obstacles and the height of the obstacle is. But in principle, you should consider this one to be precise.
We consider that 2 is the zero.
Yes, like Linear is given. What you are saying with this method is that, okay, the signal goes from here to here, and you have an attenuation. Then you keep on adding those. It's a very rude approach, but it's quite simple. So it's a first order approximation that works. Other questions? Yes.
When you talk about not very accurate for mostly space obstacle, what distance are you talking about?
I mean when the distance is comparable with the height. While if the obstacles are spaced apart, so that the distance is bigger than the height, then works reasonably well. Okay, if you want to do things with more precision, then you have to resort to the so-called Ligu method. It is called also the main edge method. It's quite different. The approach is quite different with respect to the extant Peterson. We shall see. I try to do the same geometry that is. Now this is an iterative method. You construct sub-paths. The way will be here now. First of all, you have to find the so-called main edge. That is the first step of the algorithm is find the so-called main edge. That is the edge, there are 4 edges, the edge with highest V, not the highest edge. Larger value of the Fresnel-Kirchhoff variation. And you calculate those by ignoring all the other edges. That is, as a first step you calculate. Let me use that. If this is our geometry, so we'll not mess up that picture. You first calculate the Fresnel-Kirchhoff parameter from this edge by removing all the other ones. Okay, so you draw a baseline from receiver to transmitter. Then you calculate this height, and from this height you calculate V1. This will be a different value of V with respect to the previous case, because we are ignoring the presence of all the other edges. So the baseline is different. Then you do that for the second edge. Exactly the same way. You remove this obstacle, and this is going to be H2. And then you calculate. And you go this for all the edges. Please note that if you look at the expression of V, I will not write it down again because it's on your notes. The value of V depends on the height of the obstacle, but also on the distance. So it is not obvious that the tallest obstacle has got the highest V. Because you can have a very close by obstacle that is lower than this, but it's got a higher V. So you have to find the main edge. It's not the tallest one. That's why it's not trivial. So you identify the edge with highest value. Now, in our example, let's assume that you do the calculation is easy. This is the main edge. For that main edge, you calculate losses, ignoring all the other edges. That is, you draw a straight line. Ignoring, that is removing. Other edges. Like if it was a single edge a single edge problem. So you calculate the height and you calculate V, etc. And we have it. What do you next? The next thing to do is to find the main right edge and the main left edge. Just two of them. One on the left and one on the right of the main edge. How do you do that? You do that, well, okay, here it's trivial because you have only one edge on the left. So the main left edge is this one. Left of the main edge. The left of the main edge. And then we have to find the main edge of this. And to do that, we consider the receiver and the main edge. So this will be our baseline. And you find which of those two obstacles has got the largest V with respect to this baseline. In a sense, we iterate what we have done for the main edge. We do this only once. Okay, in this case it's trivial because this is a positive edge, this is going to be a negative edge, so the V for this is going to be very small. But if you have a different kind of situation, like this, for example, you may have to compute which of the two is the right main edge. So you identify the right main edge. Let's assume it is this one. Main right edge or whichever. And once you found it, you ignore all the other edges that can be present on the scene. Just take one left, one main right, and one main left. And then you proceed as usual. You calculate the height, you calculate losses, so you end up with, we calculate with losses 0.2, this is going to be losses 0.1, losses 0.3. And we stop there, regardless of the number of edges that can be around. And we say that the total losses will be losses from the main edge, that is 2, in this case, plus losses from the main left edge, plus losses from the main right edge. And that's it. We are happy. Questions?
Pero tienes que volver la cantidad de segmentos entonces lo que calculas para ver cuál es el main es el que tiene más grande B y la B es una fórmula que da la multiplicación de la altura y la distancia no necesariamente es la más alta pero como en esa fórmula si tú reemplazas el valor de distancia este valor es negativo de
Okay, my cancel.
Cuando se me está haciendo el main edge hasta acá, esta base, aquí tenemos